Hello students, welcome to the IMS GATE Academy. So in this session, we'll continue the foundation course on computer organization architecture. So as you all are aware of the GATE Academy, the IMS GATE Academy has started the foundation course on the various subjects from all the branches. Like every day there is a session, where at least one session from all the branches. Like you understand, like the today itself, like the 4 o'clock we have a session on theory of computation, now COA, like even other branches also going on. So take the importance of this foundation course and attend and get the information, as well as share the link to your friends also, they also get benefited. Fine. So now let's continue the session on computer organization architecture, that instruction pipeline, part number 4. So instruction pipeline, I have taken 3 parts so far. So we have covered the various topics from the subtopics from the instruction pipeline. Initially we have seen some basics, followed by the performance of the instruction pipeline we have seen, and also problems on instruction pipeline, that is hazards in instruction pipeline. Like we have started data hazard, like right, data dependency, data hazard with data dependency, and control dependency, like structural dependencies are there. So initially we discussed, we focus more on the data dependency. We have seen how problem occurs, data dependency problem, how it is arises, then what are the various solutions which we can overcome. The solution was also discussed. So means now look at that another what hazard is, what control hazard, which also the cause the like performance of the instruction pipeline. This reduces the instruction pipeline. So now let us understand how the problem arises, then we can think of the possible solution for the control hazard or control dependency problem. Fine. The first will focus how the problem arises. So now what I said you so far, the previous classes, what are the things we have discussed? What are the things we discussed now? So instruction pipeline, the basics which you observed. The basics in the sense understanding what is the instruction pipeline, followed by finding the speed of factor S and efficiency of the pipeline, efficiency and throughput of the pipeline. Efficiency and throughput of the pipeline which we observed. The followed by the in terms of performance is mentioned also instruction pipeline. The speed of factor or performance of the instruction pipeline is affected by the 2 reasons. One is different stage delays as well as the dependency among the instructions, means hazards. So hazards in the instruction. What is the hazard I mentioned? What is hazard? Any condition or any state, any situation which causing the pipeline to stall. So that is a hazard or a dependency. So these hazards are like data dependency problems, or data hazard or data dependency problem. The second one is a control dependency, and third one is the structural dependency. Structural dependency. So as also mentioned clearly, so data dependency problems arises due to the arithmetic operations. Means what arithmetic operations are? Means if 2 instructions if you are executing, if the second instruction depends on first instruction, meaning second instruction requires some source operand. The source operand is the result of the first instruction, so which is not yet computed. So hence the second instruction forcefully wait for the first instruction, which increase the number of stalls in instruction pipeline. When the number of stalls are increased in the pipeline, what happens? It will affect on the speed of factor, it will affect on the efficiency of the pipeline. For that, various solutions we have discussed. So can you tell me what are the solutions we discussed? As I mentioned also, so simply you can place the stalls, placing the stall between the independent instruction. This will not minimize the time, but you can solve the problem data dependency or instruction rescheduling. So instruction rescheduling. So rescheduling means what? Placing independent instruction between the dependent one. Other approach is what? Operand forwarding. So these two are the hardware approaches, this is software approach, right? That compiler based solution also mentioned. So now let us focus on what? Control hazard or control dependency. Now please understand. So control hazard or control dependency, observe the thing all of you now. Like, so branch type instructions. So branch type instructions, causes the what? Control dependency. CD means control dependency. Branch type of instruction causes the control dependency. Sir, how it will causes the instruction? Means please understand. So the branch type instructions, alter the flow of execution, please observe, flow of execution, okay, alter the flow of execution. As a result, so pipeline need to be flushed out. As a result, pipeline need to be flushed out. Means unwanted instruction need to be flushed out. Are you getting my point? Branch type of instructions alter the flow of execution. As a result, what need to do? You have to flush it out the instruction pipeline. Means unwanted instructions might be uploaded or like fetched in the instruction pipeline, that need to be flushed out. If I flush it out, what happens? So you have to flush it out, pipeline need to be flushed out, and desired instruction is required to be fetched in the next cycle. Please observe. So due to this flushing out, what happens here? The stalls will increase in the pipeline, right? Stalls will increase in the pipeline. Okay. So due to alteration of the flow of execution, so number of stall cycle will increase in the program or in the pipeline. What happens now? When that stalls are increased, definitely there is an effect on the speed of factor, or there is an effect on the efficiency of the pipeline. So what is the things need to be understand? We have to do the solutions. We have to find out some solution to be minimize what stalls. Sir, how many stalls will happen? See, so based on how many stalls can happen, based on the instruction pipeline, based on the intelligence in the pipeline, the stall cycles will vary based on intelligence in the pipeline. The stalls will vary from please understand. So I hope this is visible. So will vary from one cycle, 1 to minimum 1 to k minus 1. Please observe, where k is a key stage instruction pipeline. The maximum stalls it can occur or incur due to this control dependency is a k minus 1 stalls. What is a k? K is the number of stages in the instruction pipeline, and minimum would be 1. Why minimum? So base intellectual means what? If I modify the data path of instruction pipeline, early stage detection may minimize the number of stalls that will observe the solutions now. So I hope you understand what I am trying to say. Branch type instruction will create a problem. So how it will create, you can observe. I am taking the example here. So program a set of instruction. Let's take instruction 1, instruction 2, instruction 3, instruction 4, instruction 5, instruction 6, like no, instruction 9, instruction 10, instruction 11. Observe 11. So this is the number of instruction. Let's take this is the branch instruction. Okay, branch. Suppose this instruction I2 is there, jump 0 or jump non-zero or jump 0. Let us take jump 0, 2000 assume that. So 2000 instruction is there. This is a jump. This is a 2000. Please observe. The 2000 address instruction 2 is there. Assumption this address is 1000. Okay, instruction 1000. Let's take this a 2-byte instruction. So let's take now 1004. This is what 1006, like this, you know. So the target instruction, let's take a 2000 assumption. What is saying that? What is instruction? Jump. Generally, please understand, branch instructions are two types of. One is conditional branch instruction, another is what? Unconditional branch instruction. Conditional branch instruction, nothing but we will check the condition, like example, if conditions, while condition, for loop. This all comes under conditional. Unconditional will be what? Go to. Simply we go to label 1, something will write. So those are high level statement, high level language, right? Now when you make it into assembly level language, equivalently what jump is, jump 0, jump non-zero. Jump is a branch instruction, please understand. Okay, jump 0. What is a 0? 0 is whatever. So accumulator value when it is 0, we always read the status of the process state. We read the status of the process register, process status word is as a register which contain all the flag registers, carry value, overflow, auxiliary bit, parity bit, like Z bit will be there. When the results, when you compute it, the result is 0, means accumulator content is 0. Now we Z flag becomes 0. When there is a 0, jump to this location meaning. Sometimes we write when non-zero, jump to this location. When we test the condition, condition is true, jump to this location. So this types of what branch instruction will they. The example I am considering. So I2 is instruction 2 is a branch instruction, jump to where I10 is a target instruction. Suppose this instruction, these are the instructions if I run in a 4-stage instruction pipeline. If I run 4-stage instruction pipeline, let's take fetch stages are fetch, comma, decode, comma, execute and store, 4 stages. And also assume that each stage of the instruction pipeline taking average number of clocks will be 1. One clock is each stage will take assumption. Okay. Now let's run the instruction this programs, this set of instruction, the 4-stage instruction pipeline. So when you fetch instruction I1, observe carefully, we have to fetch. Okay, fetch, right? We have to fetch. The fetch stage hardware, right? Is take 1 clock cycle as I mentioned, each stage taking average 1 clock cycle. Fetch. Then followed by you have to decode instruct clock number 2. Followed by you have to execute this one at clock number 3. Followed by store the results at clock number 4, right? When you are doing a fetch instruction, once fetching is over, when you are doing the decode of instruction I1, the fetch stage is free, so I can fetch what I2. So you can fetch, getting my point, fetch. Then you can decode, when you are executing, you can decode it, right? When this instruction I1 storing, you can execute this instruction, right? You can execute. Now other things, what happens? When instruction I2, you are decoding, fetch stage is free, so I3 will be fetched here, I3 will be fetched, right? So as you know, right, which we discussed earlier also. So end of the fetch cycle, please understand, end of the fetch cycle or fetch stage, the program counter will increment. So now please understand. So this is at let's take 998. Okay. Whenever instruction I1 is fetched over, then automatically PC is pointed to I2, correct or not? Whenever instruction I1 is fetching is over, program counter is pointing toward instruction 2. When instruction 1 is going on completing, then whenever instruction I2 fetch is over, automatically PC is pointed to what? PC is pointed to next instruction. So please understand, I3 is a next sequential instruction, right? Sequential instruction. Okay. Now see here, please understand, jump 0, Z flag is 0. Whenever Z flag is accumulator value is 0, jump to 2000. If it is non-zero, not required to jump, you have to go with what? Next sequential instruction only. Are you getting my point? You are getting jump 0. I mentioned jump 0. 0 means what? Accumulator content is 0. Then you have to jump to the 2000 location. If accumulator content is not 0, it is not going to be jump. Sequence instruction not to be execute only. So that's the intuition or nomenclature of the instruction I2. So I2 what is I2? I said is a branch instruction. Is a branch instruction, right? Jump 0, branch instruction. Whenever I2 branch instruction is over, fetching is over, automatically PC is pointed for I3. When you are decoding instruction I2, you are executing what? Fetching what? I3. Please understand here. If this condition is true, we are supposed to fetch which instruction? Let's take branch Z0. 0 means what? You jump to 2000 and means you have to fetch the, if the condition is true, you have to fetch instruction 10. When the condition is true, the next sequential instruction like I3, I4, I5 is not required to execute it, right? When the condition is true, next followed branch instruction not required to be executed, only direct instruction, target address instruction need to be fetched. I hope my point is clear. Now look the I2 instruction fetches over, PC pointed for I3. We don't know but whether the branch is going to be true or not, we don't know, but I3 got fetched. Reason? End of the fetch stage, PC get incremented, that is pointed to I3, I3 got fetched. Now understand. So now when results will come out, sir, like when the branch will give the results like saying that I should go target instruction or sequential instruction, end of the execution stage only. Sorry, end of this stage, end of the completion cycle, instruction cycle. End of the instruction cycle, we will come to know that the instruction to be take the branch or go to sequence instruction only, meaning you understand. Here is like at clock number 5, execution over. End of the fifth clock, will come to know. So after this instruction I2, we should run instruction I3 or I10, based on the condition, based on the Z value only. But by the time what happened? When you are decoding fetched here, when you are executing, this is going to be decode, right? It is going to be decode. I hope you understand. Similarly, I4 also got fetched here. Yes or no? Similarly, I4 got fetched or not? I4 got fetched. When execution over, means execution nothing but and execution of the branch, which verifying the condition is true or not. Now address will come end of the fifth clock only. When you are storing nothing, the generating address, you understand, getting address, to place it, right? Jump, you have to place the store nothing but you have to place into what? Program counter, or you otherwise understand, end of the stage results will come out, because end of the execution stage only, results come out. But end of the fifth clock only we will give address. We give address of the target instruction based on the condition satisfied. When you are doing this one, so this already started executing, this instruction stage is free. Other direction is decoding. Now another instruction, understand, instruction I5 also fetched over, right? You are storing means, or you end up the thing like giving some results to me. Yes, in this location address is there, or condition is not satisfied, you have to fetch what's next sequence instruction only, will come to know end of the fifth clock. By the time what is scenario happen? I3 got fetched, decode executing, I4 got fetched, decoding, and I5 got fetched. Fetch is over now. Now here observe carefully, end of this cycle, end of this one, you are going to get either target instruction to be executed, target instruction or a sequential instruction, because it is a conditional jump. Or even maybe even unconditional also, but end of the stage we are resolving the address. Now say assumption the condition is true, now we have to take the what target instruction only, means we have to jump to here, you have to jump to here, you have to jump. So which instruction you have to run? Target instruction only, target instruction. Okay. So target instruction need to be fetched. We got address of the target instruction. What is the address of target instruction? 2000 address we got. So now you have pipeline is saying that condition got true. Now you have to fetch which instruction? Which instruction you have to fetch? Next to clock means what? 6th clock. Please observe here. So next to clock, observe carefully. Now here please observe. Here end of the movement we got address. Now address what? 2000. 2000 we updated into where? PC. Program target value updated PC. So PC value now 2000 nothing but it is going to fetch which instruction? I10 or not? In the next clock it is going to fetch, next clock it is going to fetch. So in this next clock it is going to fetch. So fetch which instruction, ma? Instruction 10. This is the target instruction of the branch, right? Fetched. You are fetching this one. So means as per the semantic of the program also, if you see, if the condition is true, you have to run the target one only. If condition is false, sequence instruction you have to run. Condition is true. This I3, I4, I5 should not run at all. But what happened? Pipeline got loaded already. Yes or no? Now what to do when you are jumping for I9 to fetch, you have to flush it out the pipeline. Please observe this from this many instructions. So this many instructions, I'm just marking you, all of you ma, observe the things. Now this many instructions, sorry, so this many instruction need to be like, no, this all things to be flushed out. You have to flush it out the pipeline. Now this all things need to be flushed out. Flushed out this instruction, flushed out the instruction, flushed out the, these are the instruction you have to flush. So when you are making this pipeline is empty, nothing but fresh instruction need to be fetched. Which is a fresh instruction? Target, because branch is satisfied, you have to execute this only, right? So fetch the next clock, that is 6th clock you fetch, 7th clock decode 7th clock, at 8th clock you have to execute, at 9th clock store. This is what 9th clock. So this is happened now. Now my question, sir, you can ask me question, sir, how this is affecting the performance of instruction pipeline due to branch? This is what you understand. This many instruction you already is loaded in the pipeline, you are flushing out, that is overhead, as well as understand how many stalls are wasted. Can you tell me how many stalls are wasted here? How many stalls are wasted? You see now 1, 2, 3 are not, maximum 3, because these are parallel, this is parallel only. So 3 stalls are wasted or not? So due to this branch instruction, 3 stalls are wasted. These 3 stalls are we not able to utilize because this is unwanted instructions. We don't want to run this instruction when the branch is true. When the branch is not satisfied, branch condition is false. So obviously I3, I4, I4 need to be run. So that case it is advantage directly fetched execution. But whenever a branch is taken, condition is true, which is not supposed to be loaded or executed, but these are already loaded in the pipeline, need to be flushed out. This is creating what? How many stalls are wasted? 3 stalls are wasted here. So this understanding. So this is impacting the what? Speed up factor or efficiency of the pipeline. So due to which instruction? Branch instruction. I hope you understand the problem. Sir, how many stalls are wasted? 3, sir, in this case, because 4-stage instruction pipeline, 4th stage is address generator. I am assuming 4th last stage is giving the address of the target or sequential instruction. So now 3 stalls are wasted. But generalize, sir, K-stage instruction pipeline you are using, if last stage is address generated, how many stalls are going to be wasted? K minus 1 stalls are wasted. That's what I learned, one line I given you. Based on the intellectual in the pipeline, stalls will vary from minimum 1 to K minus 1, where K is the number of stages. Here is a 4 stages pipeline, 4 minus 1, 3. 3 stalls are wasted. Because in the problem solving, sometimes they won't mention the how many stalls happen. You have to understand based on that which stage of the instruction pipeline is able to generate the target instruction. Sometimes they say question execution stage giving the address of the target instruction. Execution stage number how much? 3. 3 minus 1 how much? 2. 2 stalls going to be wasted. But in this case what? I said 4th stage is the address generated. I am mentioning what? 4th stage address resolver. So now this what? 4 minus 1, 3 stalls are wasted. You see 3 stalls are wasted or not? Right? So this way you have to understand. Now you start think yourself. You can pause the video, things while what are the solutions can be done to improvise or minimize this, these stalls. Minimize this stalls. How we can reduce this stalls? How to avoid this what? Control dependency. Like in a data dependency we said some approach we given. So compiler time only you reschedule the instructions, that can be avoided the data dependency. Hardware approach we have seen the operand forwarding. See, it was a very intellectual method, I could say. It is about a little bit hardware support. If you give to the pipeline, all data dependency problem can be resolved. Similar way you think yourself what can be done to minimize the stalls. Yes. So means we need to look into various solutions. We need to look into various solutions now. So I am writing solution to the control dependency. Solution to the control dependency. Please understand all of you. The solution to the control dependency. Okay. There are many attempts. They did. So one is multiple pipelines. Multiple pipelines. So multiple pipelines means what is the multiple pipeline approach is saying that take 2 pipeline example. So in the two pipeline, you load it two instructions, branch as well as a sequence instruction. Based on the condition only you can decide it. We'll observe how this is going to be works. The second approach is that, so instead of multiple pipelines, hardware costly, it is cost of hardware will be more. Reduce the branch penalty. Reduce the branch penalty. Branch penalty. Penalty by early detection. Early detection of the branch. Early detection of the branch condition, branch instruction. The third one is what? The fill the branch delay slot by some useful instruction. Fill the branch delay slot by some useful instructions. The fourth step is prediction mechanism we have. So prediction mechanism, prediction. So there are these are the several approaches which we can solve the what control dependency problem. Control dependency problem. So let us see one by one how this will work. The first approach is what? Multiple pipelines. So now see, most of the cases two pipelines can resolve. Two pipelines. So two pipelines can be resolve the what? So conditional dependency problem. So what two pipeline approach is telling? Please observe here. Please observe here. These two pipelines saying that, please know, pipeline number 1, pipeline 1. Suppose let's take pipeline 1, pipeline 2. In this pipeline 1, load it, load 2 instruction, load branch instruction, target instruction. Load the branch instruction, target instruction. Here also load branch instruction next to sequential instruction. What is the problem? If the condition is true, please observe, branch condition is true. When the branch condition is true, you have to jump for a target instruction, means pipeline need to be flushed out. When condition is false, sequential instruction need to be fetched. Correct or not? So what this saying that you continue load the two instruction into two different pipelines, branch followed by target, branch followed by sequential. If condition is true, we have to run the target instruction only. So the pipeline while you continue, this you stop. If the branch condition is false, so sequential instruction need to be executed, right? Yes or no? Sequential instruction need to be executed. What you can do that case is the first pipeline you have to stop, you continue the second pipeline. What I am trying to, so again repeating. Based on the branch condition, one pipeline need to be continue, other need to be stopped. Initially both the pipelines started and both the pipelines are loaded with the two instructions. What are the two instructions? That's what I mentioned now. Branch instruction followed by target in one pipeline, branch instruction followed by sequential instruction. Both are running now. End of the stage, we come to know whether we have to take the branch condition or sequential instruction based on the condition only, right? Yes or no? I was talking about this thing only. So this will decide, here it will decide that branch will take or not. Suppose condition is true, you have to take the target instruction. So such cases, please understand what you can do such cases. So this pipeline you continue, this pipeline you continue, this pipeline you continue, this you what? Stop execution. Second case, branch condition is false, immediately stop the pipeline 1, continue the pipeline 2. So stalls are not wasted. Same time both are running or not. But what is the problem with this one? Yes, it is solving the problem. It is solving the problem, but the cost of implementation is high or not, because two pipelines required. Cost of the implementation is high. Second one, if else, please understand, if conditions are not evaluated here, means what? Nested. So what I am trying to say, nested conditions is difficult to evaluate more. Nested conditions evaluation becomes difficult here. Simple if and if else conditions can be evaluated with the two pipeline, but nested if else this condition quite difficult to do it with the two pipelines, right? So this is one of the approach. So let's do another approach. So this is like reducing the branch penalty. So this is going to be reduce the branch penalty. It is going to be reduces the branch penalty. So what is saying? Reducing the branch penalty. How you are going to reduce the branch penalty? He is saying that early detection you can write early detection of branch, early detection of the branch instruction, and first you detect the branch instruction, and early detection of the branch instruction and generation of the target instruction address can reduces the branch penalty to 1 clock cycle. So in four stage instruction pipeline which we mentioned earlier, how many stalls happen? 3 stalls happen or not? What this protocol saying that early detection of the branch instruction and generation of the targeted instruction can reduce the branch penalty to 1 clock cycle only. Is it good or not? Suppose 5 stage instruction pipeline, if the last stage is address generated, how many clocks wasted? 4 clocks, 5 minus 1, 4. 6 stage instruction pipeline, if you see, the last stage is address generated assumption, 6 minus 1, 5 clocks are going to be wasted. Like in the practical cases, if you see I7, I5 or even I9 processor having the how many stages? 14 stages are there. If suppose 14th stage, in a 14th stage, the 10th stage or 10th stage is address generated, those many clocks are wasted, and 10 minus 9 clock cycle wasted. Correct or not? Now what is saying that? Is saying the early detection and generation of the target address of the branch can reduce the branch penalty over 1 clock cycle only. Meaning, he is suggesting, this protocol is suggesting, modify the data path. Modify the data path of instruction pipeline, modify the data path at decode stage, okay, decode stage. Modify the data path of the instruction pipeline at decode stage to detect the branch instruction and evaluation of the target address that can be reduces to penalty of 1 clock cycle only. Sir, how, sir? How this will happen? Observe. How this will happen? Observe here. So I am taking the 4 stage instruction pipeline. 4 stage instruction pipeline. Stages are fetch, decode, execute and store. 4 stages are there. Now same example, if I take program has some 10 instructions, the second instruction of branch instruction and target is a 10th instruction, 3 stalls are wasted or not? 3 stalls are wasted or not? Now understand, so this is a decode stage, please understand. So you have to make the efficient pipeline here. You have to make the efficient pipeline here. We have to make the efficient pipeline. What is the efficient pipeline, sir? So what is the efficient pipeline? Please decode your decode stage. D stage means decode stage need to be modified. Modify the decode stage means this decode stage should be detect. Please understand. Detect the branch instruction. You have to detect the branch instruction as well as evaluate the what? So branch target address. Branch target address. End of the what? End of the second clock cycle only. So if you make this stage intellectual, yes, detection evaluation will happen in the decode stage only. Then you can get the address. Meaning, generally, you know, once you fetch instruction, please observe, once you fetch instruction, decode stage only will identify, yes, is it branch or non-branch, what type of instruction you will identify at the decode stage only. But some add some extra component to say, suppose you decode this a branch instruction. Now if the branch is a conditional branch, if condition or while loop or for loop condition is there, take the parameters, you have to compare, right? Now fetch the operands and apply the comparator. So comparator also included in decode stage. The comparator will compare the 2 operand, it says yes, less than or equal, greater than or equal, whatever function you given. It is saying that yes, true or false. Based on the results of the comparator, address can be generated at the decode stage only. So hence, So we can reduce the branch penalty by 1 clock cycle. Observe here. Let's take instruction. So now I am taking same example, instruction I1 fetch, instruction I1 fetch, okay, followed by decode, then execute, then you store, right? Clock number 1, clock number 2, clock number 3, clock number 4. Yes or no? Once instruction I1 fetch is over, I can fetch. This is a branch. So jump 0 is a branch instruction. I fetched here. Observe. I fetched here. Then here it is what? This is fetching is over. So this fetching is over, right? Fetching is over. Then I am decoding. Okay. So now this decode stage of, please observe, decode stage of the, whenever you decoded this branch instruction, conditional branch instruction. Now end of the, please observe. So when you decoded, observe what happens here. Whenever you decoded, instructions decoding or comparison happening, I3 already fetched, right? I3 instruction fetched here. Yes or no? This is a sequential instruction which suppose the branch condition is satisfied. So now I3 instruction is not required to be fetched. I3 instruction is not required to be fetched. Getting my point? I3 instruction should not fetch. You would jump for target instruction. You would jump for target instruction only. Now what you have we made this decodes is much intellectual. Whenever you detect this branch instruction, immediately fetch the operands and do the comparison, generate the address. Now end of this, please understand, end of the decode stage only, we are deciding you have to fetch a sequential instruction or target instruction. If the condition is false, means what? Branch condition is false. So you have to run what, which one? Sequential. But sequential is already fetched here. Sequential instruction what? Sequential instruction already fetched. No problem, no penalty at all. No penalty. The branch condition is false, sequence instruction already fetched, that is required to be fetched only, but no penalty. That's good only. Whenever condition is true, you have to execute what? You have to fetch target instruction only. But you know, target address will come here only. So immediately next clock, please, the end of the 3 clock, we got address. Let's take situation I'm taking. Branch is satisfied, we have to run the target instruction only. End of the 3rd clock, we got a address of the target instruction, that 2000 in the example which I mentioned. So now it is going to fetch what target instruction only here. Next to clock, it is going to fetch which instruction, ma? Which instruction is going to fetch here? So which is instruction is going to fetch here? So it is going to fetch what? Target instruction. Here this is a target, okay? Target. Fetch the target instruction. Then you have to decode this instruction. Decode. Then you do the execution store here. Now see, so how many instructions need to be flushed out? How many instructions need to be flushed out from here? How many instructions need to be flushed out? Only one, is it not? So this 1 clock only. How many clocks are wasted now? How many stalls are wasted? Only 1 stall or not? Only 1 stall is wasted or not? I was telling same thing. Early detection of the branch condition, evaluation of the target address will minimize the branch penalty equal to 1. Because see, just first stage, fetch stage, you cannot do it, because fetching instruction from memory will happen. In the next cycle only you have to generate the address. If you are able to do it that one, branch penalty will be only 1 clock cycle. Yes, we did. End of the decode stage, we got address. Whenever condition is true, you have to fetch the target instruction. That address will place in program counter. Program counter will fetch the target instruction. Now only 1 instruction need to be flushed out. Only 1 clock is wasted here. Now understand, k-1 clocks to be reduced to 1 or not. That's what one line I given. Please mark it, that important line I mentioned. Based on the intellectual and instruction pipeline, stalls can vary from 1 to k-1. The best case will be 1, worst case will be k-1, because we modified the which stage? Decode stage we modified. So now 1 stall is wasted here. So now is it better than, is it far better than what? Multiple pipeline or, because multiple pipeline is great, I can faster, I can say, because hardware cost is duplicated here. 2 pipelines required to implement. Now we are not taking any pipelines, we are just modifying the, so data path of instruction pipeline is existing one, that will minimize what? Penalty of 1 clock cycle only. Yes, I am obey with 1 clock cycle, so I can deploy what? Early detection method. Can I modify decode stage? Yes, this is one of the approach we can tell. So later people again thought of it. So how to minimize this one also, or if not able to minimize, how to utilize that? What is overhead is here? What is the overhead? At least here 1 instruction need to be flushed out. Whenever a branch condition is true, so those times the 1 instruction need to be flushed out. You have to fetch instruction, you have to flush it out, correct? This flushing and flushing, the fetching and flushing is happening for one instruction or not. This is also override is there. Now people thinking that, so why should I fetch this instruction? So now compiler time, so they modified the solution, please observe. So they modified the solution. So they made into what? Third approach, branch delay slot. What is the branch delay slot? Nothing but compiler time, please observe. Compiler time. So compiler time, okay. So now, so what I'm trying to say here, better I'll first of all I'll write, okay. So now here reducing branch delay slot or early detection is override is what? We have to fetch one instruction, the sequence instruction, you have to flush it out. Please understand. Fetching and flushing out of an instruction equivalent to what? So we can introduce a no instruction, mean please understand I'm writing. So compiler place the nope instruction, place the nope instruction after branch instruction, after either branch conditional or unconditional, after branch instruction, okay. So which is equivalent, please I'm writing, placing the nope instruction after a branch instruction is equivalent to fetching of instruction, flushing out from the pipeline, both same, meaning same only. But if I keep it nope operation compile time, what happens? So the overhead of the pipeline can be reduces. How, sir? How this is going to be reduces? Suppose program is there. So program is there having instruction 1, instruction 2, instruction 3, instruction 4, instruction 5, instruction 8, instruction 9, instruction 10. Total 10 instructions are there. Now observe. So this is jump 0 to 2000. Observe now 2000. Now at 2000 I8 is there, means you understand I8 is a target instruction, I8 is a target instruction, okay. This is a branch instruction, this target is what? I8. Getting all of you now. Now what happens if I run this program in like a efficient pipeline? What is efficient pipeline? Modified pipeline. So one delay will be there, one delay will be there, right? One style clock cycle going to be wasted. Another thing, what? Overhead of this one. So this how overhead can be minimized by introducing the nope operation. Same program only, compiler going to be modified it. Compiler going to be modified. What a compiler will do? Instruction I1, instruction I2 is a branch jump 2000, right? 2000. Now here I am making what? Nope operation. Only one nope operation I'll keep it, followed by I3, followed by I4, I5, then this is I8, I9, I10. That's it. Now this target is what? This only target instruction at 2000 in memory location. Fine. So this is modified by what? Compiler. This code will be modified by compiler. What I did, simple. You just identify branch instruction. After branch, you place a nope operation. That's it. This is the instruction. Please, nope operation instruction. What is the meaning? Whenever nope is encounter, no work. Like so whenever you fetch a nope operation, further you won't proceed. Further decode execution won't be there at all. Just your fetching only. Fetching instruction means like no means what happens? You fetch instruction, further won't be there, right? Means what is further won't be there? No headache of the what? Flushing out of the instruction pipeline. Here is you fetch I3 when instruction decoding generating address of the branch instruction. By the time instruction I3 fetched, whenever target address generated, before jumping you have to flush it out. That headache will not be there. So this also can be minimized. Yes, this is good thing. Correct or not? Yes. Now headache we removed. This is what? Branch delay slot. This in a branch delay slot. In a branch delay slot. What I placed here? In a branch delay slot. What I placed? Nope operation we placed. Nope operation we placed it. So then later, please understand, later some time, after some years you understand. So why can't you utilize this slot? Why should I place it only nope instruction? So can I reschedule means what? That's what things which we did for operand forwarding. Rescheduling of instruction means out of order of execution. Instead of keeping no operation, some useful instruction you place it here, so that can be run. So means what? Find out some independent instruction, one instruction, and move to branch related slot. So what happens? It will increase what? Throughput or not? That's what. So instruction rescheduling. instruction rescheduling. So next they modified instruction rescheduling. So instruction rescheduling. So this should be done by what? Compiler only. Meaning, please understand what is the meaning here. So nope instruction replaced by what? Some useful instruction. Some useful instruction. Some useful instruction. Useful instruction and independent instruction here. So what does mean? Suppose, please observe here. Program as instruction I1, instruction I2 is a branch instruction jump 0, Z0 at 2000 something is there. So I3 instruction, I4 instruction, getting my point. This is I8, I9, I10 is their assumption. Now at 2000, I8 is there. The target is what? I8 only, right? Yes or no? I8 only. Its target is what? I8. Observe. Now, compile time what he did? This we modified. I1, I2 followed by, here is a nope operation was there. Nope operation followed by I3, I4, then I8, I9, I10, right? Yes or no? So this is what? Branch delay slot. This is what? Jump Z 2000. It's an instruction. This is a 2000 instruction. Okay. This is the first one is there. One clocks will wasted. That will be headache is minimized by keeping nope operation. This again further dividing, like modifying instruction I1, instruction I2 in the branch delay slot. Okay, let's take I3, I4, let's take I5, I8, I9, I10. Let's take suppose assumption I3 is just our independent instruction assumption. This is independent instruction, no dependencies there assume that. So what I will place it here? I9 I will place it here. I9 I am placing here. So now branch delay slot filled by what? I9. So this won't be there now. So now you understand the here I8, I10 only there. Now here is the branch jump 0 to 2000, right? So it is jumping here, say 2000 place, I8 is there. Now understand what I fill with the branch delay slot? Fill it by I9. In the branch delay slot we fill it by I9. I9 is a useful instruction. Now see, so I9 are not required to fetch separately. So this can execute along with this I9. Now pipeline flushing out is not required. Simply reordering we called. So this is what in order. This is what reordering means. What? The scheduled. So as a programmer given some sequence, I modify the sequence. Simply compiler had to identify some independent instruction, place it here. So yes, pipeline instruction pipeline support is what? Reordering of the instructions. You can change the order, but you have to preserve the semantic of the programmer. That need to be understand clearly. Yes. So this is clear, ma? All of you. This line is clear, right? So this way we can solve it. So you can useful thing you can done. So this is what branch delay slot useful by, like placed by what? Some useful instruction. Some examples I want to show you. Example 1. You see the example 1. Now here branch delay slot. This is the program code is there. R7 equal to R2 plus R3. If R2 equal to 0, then go to label here. This is the target instruction. You see, this is a target instruction. Branch this target. Now branch followed branch delay slot. Which instruction can be moved here? Can you suggest me? Which instruction can be moved here? Which instruction can be moved here in the branch delay slot? Can I move it this R7? So yes, I can move it or not. So now, so I can write R7 equal to, because this independent instruction only, right? R7 equal to R2 plus R3, I can write it. So this you can remove and move it here. Yes or no? The branch delay slot we can move it. This example. Look at example 2. Now tell me which instruction can be moved in a branch delay slot? Which instruction can be moved in branch delay slot? Means you understand you have to modify here. So now R1 required, but this is not required, right? So what I can do? R1 equal to R1 minus R2. If R1 equal to 0, then go to L. When the condition in a branch delay slot, what I'll move it? So L equal to R4 equal to R5 plus R6. Then some other instructions here, instructions. Yes, that's it. So I moved here. This is a branch delay slot. Yes or no? So independent instruction, right? No dependency. When condition is true, already we have fetched this instruction. Already we fetched this instruction. Correct or not? Similarly, there was a question in the GATE paper. They asked this question. So which the following code is to be run in a pipeline processor with a one branch delay slot. They said one branch delay slot. Now these are the instructions are given. Which of the above instruction fill the delay slot I1, I2, I3, I4? In the delay slot, which instruction can be placed? Think, answer it. Yes, which instruction you can place it here? Which instruction can be placed here? So I1 saying that add R7, R8 storing R2. I2 saying that R5, R6 subtract you store in R4. I3 saying that R2, R3 add storing R1. So now see, so understand this R2 source operator means it depends on this one. I3 depends on I1. So I1 should complete before I3. So I1 you cannot move it here, correct? I1 you cannot move it. The store R1 results in M of R4. So means this is depends on this one. R4 computed by what? This I2. So I2 also here only. What does mean? I4 depends on I3, I4 depends on I2. Meaning I2 cannot run after I4. Even I3 also cannot run after I4. So I1 also cannot run after I3. So which instruction can be moved here? Can you think? Independent instruction means no dependency. Dependency you have to remove it. So can I move? So this is I5 is a branch instruction. He is saying if R1 equal to 0, then label to somewhere target instruction. So now this has to run only after this 3, right? So I can move it here. I4 I can move it. Yes, simple. Option D is the right answer for this question. Yes or no? We can move it or not? Yes, absolutely we can move it. So I4 instruction can be moved in the branch delay slot, so that now this can be utilized here. This type of question they can ask, right? So far how many solutions we have seen? One solution, multiple pipelines. Second is a branch, reducing the branch penalty. Third one, branch delay slot. The next one is a prediction method, I said. So before going to prediction method, let's see some questions on this one. Let's see some questions on this one. Okay. Let's see some questions on this one. Okay. Now observe the question. This question was asked in GATE 2013 paper for 2 marks. GATE 2013 paper in 2 marks now. Consider an instruction pipeline with the 5 stages without any branch prediction. So branch prediction not there. Fetch instruction, decode instruction, operand fetch, execute instruction, and write operand is there. The stage delays for these are the instructions given 7, 10, 8, 6 nanoseconds respectively. So there are intermediate storage buffers after each stage, and the delay of each buffer is 1 nanosecond. A program containing 12 instructions. A program contains 12 instructions I1 to I12 is executed in this pipeline processor. Instruction I4 is the only branch instruction. Out of 12 instructions, I4 is a branch instruction. I4 is a branch instruction. Its branch target is I9. Its branch target I9. If the branch is taken during execution of this program, if branch is taken during execution of this program, the time in nanosecond needed to complete the program is dash. How much time is required? How much time is required to complete this program? They are asking. Option A 132 nanosecond, option B 165, option C 176, option D 328 nanosecond required. Let's run this one as per the given things. How many instructions are there? Program has I1 to I12 instructions are there, right? Sorry, I'm right. I1, I2, I3, I4, I5 like this, I12 instructions are there, right? I4 is a branch instruction, right? Sorry, I2 is instruction, right? I4 is a branch instruction. So this is a branch instruction one. This is a branch instruction. Its target is what? Target instruction. What is the target? I9. So somewhere here is I9. I9 is a target instruction. This program they have run in what? 5-stage instruction pipeline. 5-stage instruction pipeline. What are the stages? Instruction fetch, instruction decode, operand fetch, execute instruction, write operand, right? Write operand only, write operand, yes. 5 stages, 1, 2, 3, 4, 5 stages. The stage delays also they given, stage delays also given. Now they have run in this pipe, this program they are running the program. This one, the branch has taken, they said, branch has taken. They said if the branch is taken during the execution of this program, branch already taken, please understand, branch has taken. So branch has taken means penalty will happen or not. So let's run this program. Let's run this program. I'm running instruction I1, please, instruction I1. So now stage delays given. What I'll do, stage delays given in terms of time given. So let's go with what? Cycles only. Now later cycle time of the pipeline can be find out. What is cycle time of the pipeline? Maximum stage delay plus buffer overhead we know. Correct or not? So through time you cannot go stages. What you can do? We'll go with the clocks only. So assumption is what? In the pipeline what average clock per instruction will be 1. The 1 clock cycle time will be what? Maximum stage delays only can be taken, right? So instruction 1 I'll fetch. Instruction fetch, right? Instruction fetch. So taking 1 clock cycle, then instruction decode, taking 2nd clock, 3rd clock operand fetch, 4th clock execute this instruction, 4th clock, and the 5th clock. 5th clock is what? So 5th clock write back operand, right? At 5th clock, this we know. Similarly, whenever instruction 1 decoding, so this instruction I2 can be fetched. So instruction fetch, I can do instruction decode here, operand fetch here, execute this instruction can be done here, then write back operand will be here. Okay, clock number 6. Similarly, instruction I3, instruction fetch, instruction decode, operand fetch, execute this instruction, write operand. Okay, clear? All of clear? Clock number 7. Observe now. Now next one, what? Instruction I4. What is I4 here? I4 is a branch instruction. I4 is a branch instruction. Now I4 instruction branch instruction is fetched, instruction decode, operand fetch. This is executing. What they said, branch has taken during execution of the program is what? The instruction when executing, when the program is executing, branch has taken. So now please understand, this stage will here, this stage is the address, target address will give, target address will produce here. So target address produced by which stage here? Not write back, end of the execution stage only we are getting here. Correct or not? Branch has taken also said, the branch is satisfied also they said here. Now it will go into a target instruction, but you know when you will get address, end of the 7th clock will get, but by the time what happens here? By the time what happens you observe here. So whenever instruction decoding here, instruction decoding, so instruction I5 is fetched or not? Instruction I5 is fetched, then instruction this is decoding, operand fetch is happening here, yes or no? Operand fetch is happening. And also you observe now instruction I6, instruction fetch, instruction decode is done here, decoding is doing on. Now here what happens? I7 instruction, so instruction fetch also happen. So end of this clock, please observe, end of the clocks is target address, we got it jumping to where it is going to fetch the target instruction. What is the target instruction? Is it not I9? Target instruction is I9 or not? Instruction I9 is going to fetch here, please observe, I9 we fetched. At 8th clock instruction fetch of I9 happened. So instruction decode 9th clock, 9th clock, then so instruction operand fetch, then execute this instruction followed by, so write operand here, clock number 10, clock number 11, clock number 12. Now, whenever instruction I9 fetching is over, when you are decoding at 9th clock instruction I10 I can fetch it. Yes or no? At clock number 9 I10 I will fetch it. Clock number 10 I11 I fetch it. Clock number 12 I will fetch what? Clock number 11 I will fetch what? At clock number 9 I will fetch what? I9. So I10. Then when it is running at clock number 10 I11. At clock number 11 I12. So now see, so when they are going to complete, if I continue, so next to 3 instructions are there. At 13th clock I10 will complete. 13th clock I10 will complete, right? So 14th clock I11 will complete. 15th clock I12 will complete. Yes or no? Yes or no? Are you able to understand? Now see what I am trying to say here. So now, so number of clock cycles. Number of clock cycles required. How many? 15 clock cycles. I hope you understand this point. I hope you understand. See, yeah, so yes, spacious issue I'm not able to write, but meaning you understand. So 12th clock I9 completed. 12th clock I9, 13th I10, 14th I11, 15th I12. Please understand. When you jumped also you understand this many instructions need to be flushed out or not. How many stalls are wasted here? 1, 2, 3. 3 stalls are wasted. Yes or no? Otherwise understand, instruction executed the 4th stage pipeline. 4th stage address generator 4 minus 1. 3 stalls are going to be wasted or not? Yes or no? 3 stalls are wasted. So in this way you can calculate number of clock cycle required 15. Now time required, right? Time they are asking time for this program. 15 clock cycles only. But clocks, but in terms of time we need to find out in terms of time. But they given na clock period, how to get the clock time, cycle time of the pipeline which we discussed earlier. Whenever stages are different times given, cycle time the pipeline will be maximum of stage delay. What is the maximum stage delay? So now they said, so 5 nanoseconds, 7 nanoseconds, 10 nanoseconds, 8 nanoseconds, 6 nanoseconds, and buffer delay is 1 nanosecond. Maximum stage delay was 10. So 10 only 10. So 10 plus 1, 11, right? Now 15 into 11 will be how much? 165 nanoseconds. Yes, this way you can answer the question. So 165 means option B is the right answer. Option B is the right answer. This way you can answer it. So you have to draw, please observe, you have to draw the timing diagram. You observe, very simple, no? Normally drawn. So one by one by run. So I4 is jumped here, this we flushed it out. So I calculate the number of clock cycles. So this also can be done simplerly. So this also can be done simplerly. Please understand how that can be done. So now what you have to understand. So first this one, observe here. When the first instruction is completing, at 5th clock, I'll write I1 instruction will complete after 5 clocks. When I2 will complete, 5 plus 1, yes or no? When I3 will complete, plus 1, yes or no? You go and see. When I4 supposed to complete plus 1 only. I4 supposed to complete plus 1 only. But it's a branch instruction, right? So I4 is jumping to where? I9 jumped. Then you have to run I10. Then you have to run I11. Then you have to run I12. Then I'll do C. So I1 5 end of the 5 clocks. I2 6th clock. I3 7th clock. I4 should complete at how much? 8th clock only. But this is a branch instruction. It got jumped. So due to jumping here, how many stalls are happened? 3 stalls are happened. Please understand. Now we will complete here. So then I add it 1, 1, 1, 1, 1. So now understand here. So now after this one clock only I10 will complete. Then after 1 clock only this will complete. After 1 clock only this will complete. Now count the number of clock cycles. 5 plus 1, 6, 6 plus 1, 7, 7 plus 1, 8, 8 plus 3, 11, 12, 13, 14, 15. Yes or no? So 15 clock cycles. You got it or? Yes or no? Clock time, how to get it? So maximum stage delay, that is 10 plus 1, 11. So this giving 165 nanoseconds. This also way you can solve it. So now see here 5, 1 plus 3, 4, 4 plus 1, 5. So due to this branch instruction, 5 clocks are full pipeline. You have to flush it out. You have to flush it out fully. You have to run or not. See, whenever, see, branch instruction, end up the execution target address you got, right? You have to, entire pipeline, you have to flush it out, you have to start from beginning. Beginning, nothing but all stages you are running, five is happening or not? 5 plus next extra instruction. That's what you understand. 3 plus 3, you see 3. Here 3 is the stalls, 3 is the stalls. Now how many are the 1, 2, 3, 4, 5? So otherwise you understand 3 added here, that's it. So now here is a 5. Here is a 5. How I did 5 here? Simply, I have did 1 plus 3, 3 plus 1, 5. That meaning. So this way also you can solve it now. I hope you understand the way problem solving. The prediction method I will continue into next session only, ma. So thank you so much.